this video, I'm going to do an overview of some basic concepts from our forces unit. So first part is the types of forces. And here we just have our list of them. So we have the force of gravity, and the force of gravity always points down. We have a push or a pull force. This is just a generic. If someone's pushing, someone's pulling. If it's not any of these other specific types, we call that a push or a pull force. The force of friction, that tension should not be there. This is the force of friction. The force of friction, the rules with that are the friction is always going the opposite direction that the thing is going to be going. It's always going to work against you. And it's always parallel to the surface. So for instance, if we have a table here and we have a box, and maybe I'm pulling the box this way, the friction is going to work against me, or it's going to work against the motion of the box, not against me. It's going to go against the opposite direction that's sliding, so that would be the force of friction, and it's parallel to the surface. The friction is not going to go up, and the friction is not going to go down like that, unless the surface itself would be slanted. Another force we have is the normal force, and remember, this force is a kind of a support force from a surface. So anytime we have something sitting on a table, we have a book on a table, we have a force of gravity on that book, but then we're also going to have a normal force on the book by the table. That's why the book doesn't crash right through the table. This could also be on a wall too. If I take and push something against the wall, the reason it doesn't go through the wall is because of that normal force. And then lastly, we have the force of tension. This got moved over here. So force of tension. Tensions come from strings, cables, ropes, all those kind of things. So down here, there's a list of questions you can ask yourself every time you draw an FBD to figure out which forces are there. One other thing is that you want to draw the forces acting on the object. So for instance, if we have a car on the road, there's my car, a lot of times students will think, oh, the car is pushing down on the road, the car is squishing the road. And that's true, but we only want to draw the forces that the car feels. So the car actually feels the road pushing up on it and the force of gravity pulling it down. So we always want to draw the forces on the object, not the forces that the object is exerting. So that's the background on forces. We have three big physics concepts here with Newton's laws. So physics concept number one, how do objects experience a net force? So net force is not a force. It is just the answer when we add up or combine a bunch of forces. Another way to think of it is there any force left over? If there is, then we have a net force. If there isn't, after we combine all the forces, if there's no force left over, then we don't have a net force. So the net force is zero when all the forces balance. And what we mean by that is if we add up all the forces going in one direction, let's say left, and we add up all the forces going in the other direction, right, we're going to get the same value. So for instance, let's see how well I drew this to scale. If I move this one over here, move this one over here, that's pretty close. The idea is if I have 100 newtons, newtons is how we measure force going right, then I would have 100 newtons going left. And it's not the number of forces, just the total amount, the total strength. So if those strengths are balanced, then we say that there's zero net force. If they're unbalanced, so for instance, maybe we had two forces going this way, but one really big force going to the right, in this case, our net force, which we don't draw on the diagram, but we have more force going to the right than to the left, so our net force would point to the right. Another way to say this is the sum of all the forces. That just means add them all up. So the forces are balanced if all the forces pointing left is equal to all the forces pointing right. Or we can look up and down as well. So we can say all the forces going up versus all the forces going down. That is going to give us a net force of zero, and we're going to say the forces are balanced. Now, if that's not true, then we have a net force, and the forces are unbalanced. So that means when we add up all the forces going up minus all the forces going down, we don't get zero, and likewise for left and right. We choose our positive and negatives, so we just steal those from the math teachers. So this would be like positive x and negative x. So anything going to the right would be a positive force, anything going to the left would be a negative force. And this would be positive y and negative y. So all the forces going up minus all the forces going down. And we just get that from the Cartesian coordinate system. All right, so some examples here. On this force diagram, we have 0 forces going left and right. There's nothing there. And so the net force, the sum of all the forces, what's left over if we add up all the forces going left and right is 0, because there are no forces. And then in the vertical, what we should have is tick marks on these. All the forces going up are equal to all the forces going down. And so they add up to 0 as well. That's example number 1. Example number 2, we see a similar thing. All the forces going up is equal to all the forces going down. All the forces going right is equal to all the forces going left. So the net force is 0. Now example 3, all the forces going up and all the forces going down. I'm putting congruency marks there. It's like from geometry. They still add up to 0. But in the net force in the x direction is not 0 because this force here is larger, it's stronger. The arrow that we use to represent the force is longer than the force going to the left. So we would have a net force, an unbalanced force that points to the right. And in example number 4, no forces acting left to right, so that net force is 0. And the force going down is larger than the force going up. So we have a net force that would point down. So that's how we look at net force. If you're struggling drawing FBDs, there is another video that will show you how a bunch of examples of drawing FBDs. All right, physics concept number 2, when do objects accelerate? This is the one that everyone thinks is really easy, and then they have to answer questions on it and they get them all wrong. So just a heads up here. So if an object is at rest, it means it's not moving. It means the net force on it is 0. I think that is pretty intuitive. This one here is the one that everyone messes up. If something is moving with a constant velocity, the net force is still 0. So the classic example is you have some rough ground here and I have a box and I'm pushing the box, I don't know, to the left with some constant velocity. So constant velocity means the net force is 0. We can do the verticals first. There's force of gravity, and it's not accelerating going up and down. There's nothing happening going up and down, so those are going to be the same. Now, the wrong answer that everyone says is they say, oh, since it's moving left, my push force going to the left has to be bigger, and this is wrong, bigger than my friction force. It's incorrect. To go at a constant velocity, you don't need an unbalanced force. So in this case, the push force is equal to the friction force. Why do we always think we need to keep pushing something with a bigger force? Because there's always friction there. But we actually just have to measure, or we just have to match friction. Another example is if there is no friction. Let's say, I think like we had a hovercraft in class. Again, we have a normal force and a force of gravity. Nothing really going on in the vertical. Now let's say the hovercraft is moving to the left at a constant velocity. Most people incorrectly, this is wrong, say, oh, well, the hovercraft was pushed. To get the hovercraft going, we did need to push it. But now that it's already moving at a constant velocity, it does not require a push. I do not need to keep pushing it. And I can't affect it unless I'm touching it. I can't stop that hovercraft without touching it and pushing it, so I can't keep it going unless I'm touching it and pushing it. If the Earth was perfectly smooth and this went on and on and on and on forever, I would not need to keep pushing the hovercraft to make it keep going. Also, it keeps going without me using any of my strength. So a lot of times students think, well, the push goes with it. That's not true. I have to be touching it, and the hovercraft will keep going and keep going and keep going, and I'm not going to get tired because I'm not exerting a force on it if I'm not touching it. So those are the two examples that always trip students up. The last example is acceleration. What happens if the net force is something's accelerating? This is a changing velocity. That could be going faster and faster, and, or that could be going slower and slower and slower. Acceleration does not mean only faster and faster. It's faster and faster or slower and slower. So if the net force is not 0, so we have more force going in one direction than the other, then we will have an acceleration. We will change our velocity. These two examples were the same exact velocity the entire time. Velocity was not changing. And this is where we are going to go faster and faster or slower and slower. All right, so net force causes acceleration. So this is a cause and effect. So we have a cause, if we have a net force from an unbalanced forces, and the effect is our object will accelerate. Some rules with this. If net force is 0, then acceleration is 0. If net force points to the right or up, so our positive directions from our Cartesian coordinates from math class from a graph, then acceleration points to the right or up. If net force is negative, then acceleration is negative. This is because F net causes acceleration, they always point in the same direction. So net force and acceleration always point in the same direction. All right, so from physics concept number 2 box, the biggest things here is if something's moving at a constant velocity, the acceleration is 0, and that means the net force is 0. Net force causes acceleration, so if you have 0 net force, you have 0 acceleration. And then net force and acceleration always point in the same direction. All right, last one, physics concept number 3. When do accelerating objects increase speed and when do they decrease speed? So here are the rules for that. So when do objects increase speed? It's all about velocity and acceleration. So when velocity and acceleration point in the same direction, the objects are going to increase speed. Let's switch to a different. When do they decrease speed? Well, when velocity and acceleration is always about those two, point in the opposite direction, they're going to decrease speed. When do you remain at rest? When your velocity is 0 and your acceleration is 0. And when are you at a constant speed? Well, when only your acceleration is 0. So your velocity isn't changing and your velocity is not 0. So if we zoom out here, what are you going to be expected to do for our explanations? One, you're going to be expected to draw an FBD and label with the appropriate types of forces. Then you're also going to be expected to determine if there is a net force on the object or not. Kind of the third step in the thinking is determining, based on the net forces, is your object accelerating? That is it changing velocity or is it not changing its velocity? Using that, you can figure out the direction of your acceleration. So, I know it's accelerating and net force points to the left, so acceleration points to the left. And then the last step is then comparing the direction of the acceleration to the direction of the velocity to say if the object is increasing speed or decreasing speed. And that's a cause to effect order. The other thing we can do, so we're looking at forces and we're seeing, okay, what happens? Are we increasing speed or decreasing speed? We can also go in the opposite direction. So for instance, we may tell you that something is decreasing speed. So then you need to apply this physics concept that, velocity and acceleration must be in opposite directions. That means that the net force and the acceleration, the net force and acceleration are always in opposite directions, but then that means your net gives you the direction of your net force. You also are going to know from the given that, we're changing velocity or have a constant velocity. Once you know the direction of net force, you're going to know, maybe the forces to the right are bigger than the forces to the left. And you'll be able to figure out one of the missing forces. And you're going to need to be able to think through that and write an explanation for that. To help you, on the next page here, we have target sheet number 2, and it kind of gives the thinking through this. So this is cause and effect. So if we're starting with the relevant forces, that's the cause. So, relevant forces to combine to produce a net force or 0 net force on the object. Then based on the net force is going to make an acceleration. So this is what you talk about. First you talk about relevant forces, then you talk about, what does this mean about the net force? What does this mean about the acceleration then? And then you can say what this says about the velocity. Either we're speeding up or we're slowing down. The opposite direction for that is effect to cause. We may tell you, oh, object is speeding up or object is slowing down. And that's going to tell you the direction of the acceleration. From the direction of the acceleration, since acceleration is created by net force, caused by net force, we know that they point in the same direction. Then once we know something about the net force, direction of the net force, that's going to tell us, oh, this force is going to be bigger than this force, or oh, these two forces are the same. The relevant forces are going to be the forces that are parallel to like the direction of the motion, or the forces we're asking about. So if we're asking about a horizontal push force, you don't really need to talk about gravity and normal force. If we're pulling up on something with tension, you don't really need to talk about the horizontal forces. All right, so there's the overview for our explanations part of this unit.